which one? Oh, Zoom?
Yeah.
Or do I have to quit and reopen?
Yeah. It's all right. I got credentials.
Do you want me to get the application?
Yeah, go for it. Won't be a second, ladies and gentlemen. Technical issues.
To log in again into Zoom.
Yeah, Zoom didn't like it. Should have scheduled a little more time for the transitions. But you're a loudspeaker, so.
Kind of grab a few more minutes.
Yes, exactly. Actually, the schedule I noticed right now is 2:15. I mean, sorry, 12:15 actually
For lunch.
for breaking for lunch.
Oh, okay, well, 15 minutes late.
Okay, now in fairness, I cannot.
Enjoy, Hayden.
Okay.
Yep.
So I think we're ready
Yep.
to roll.
Okay.
Thank you.
Okay, so first of all, I'd like to thank the organizers for the opportunity to present this work today. And I'm going to be talking about superfluids in two-dimensional Bose gases. So we've already heard one talk about Bose-Einstein condensates yesterday by Peter, where he's introduced some of the ideas. So I do not need to repeat many of the things that he said, except to add that just these superfluid systems provide sort of ideal paradigms for studying dispersive hydrodynamic phenomena, because when you go to very low temperatures, dissipative effects are essentially suppressed, and then sort of dispersive effects become sort of prominent. Now, my interest in the these types of systems for this particular talk stems from the fact that in recent years it's been possible to realize Bose-Einstein condensates in low-dimensional configurations by effectively freezing out the degrees of freedom in one or two of the coordinate directions. So this sort of opens the way to sort of study fundamental physics in low dimensions. So for example, you might be interested in how a Bose-Einstein condensate forms in low dimensions. And this has been known to be associated with what's called the Berezinski-Kostelis-Taulus transition that was first formulated in the 1970s. And subsequently, two of the people mentioned there, Kostelis-Taulus, were awarded the Nobel Prize in Physics in relation to some of this work. But it turns out that vortices, so I should say this BKT transition is associated with what's called a vortex-anti-vortex unbinding. And that leads to sort of the emergence of long-range correlations and formations of BEC. But it turns out that vortices also play an important role in 2D systems when you want to understand the nonequilibrium dynamics, which is what I'm interested in for this talk. Okay, so this is going to be the focus. And 2D systems are special because these vortex excitations are in some sense topologically protected, which means that once you introduce them into the superfluid, there's no way to sort of get rid of them unless you annihilate them with an anti-vortex, a vortex of opposite sign, or you move them at the boundaries. And they also have long-range interaction. So if you think of the vortex excitations as making up sort of a subsystem in its own right, a gas of vortices, then you do not have sort of the thermodynamic limits depend on how you sort of take the limits because of the long-range interactions. And they can also give rise to associated conservation laws. Now, we've already heard that sort of the typical model that's used for this kind of problem is the Gross-Pitaevskii equation, which is the main working model I'll be using for this talk. And it's essentially going to be a 2D nonlinear Schrödinger equation of the defocusing type with an interaction potential G. But this interaction potential is going to be sort of renormalized because you have to account for the fact that you've integrated out the degrees of freedom in the other coordinate direction. Now, because we're going to be talking about vortices, it's useful to make the connection with the hydrodynamic picture through the Madelung transformation, where we basically relate the macroscopic wave function for Bose-Einstein condensate in terms of an amplitude and a phase representation. And so the density of the superfluid can be defined as the atomic mass of the species times the amplitude squared. And the current can be related to the gradient of the phase. And so you have essentially an irrotational flow for a superfluid because the phase is like a velocity potential. And so this complex equation can be mapped into two real equations, the continuity equation for a compressible fluid and an unsteady Bernoulli equation, where the pressure dependence is such that it depends only on the density. So what you have essentially is a barotropic fluid. And you have this additional sort of term that's typically referred to as the quantum pressure term. And that's what makes these systems different from the classical counterparts, because this is where the dispersive effects are encoded. Right, now if you consider plane traveling wave solutions for the Gross-Pitaevskii equation or the defocusing NLS over a uniform background, then you get this dispersion relation, which in our community is referred to as the Bogoliubov dispersion relation. So at low wave numbers, you have essentially a linear relation with wave numbers. So that's essentially the speed of sound within the condensate. So these are what you might refer to as phonon excitations. And then at higher wave numbers, you have the free particle spectrum. But in addition to these plane wave solutions, you can also have vortex excitations. And so these are nonlinear excitations, and they are solutions of the Gross-Pitaevskii equation. And they are essentially associated with phase defects or phase singularities. And basically, when you're sort of located at one of these vortices and you go around, you sort of pick up a phase winding of an integer multiple of 2 pi. Now, the vortices themselves have an associated core structure. So basically, where the density is depleted within the center of the vortices. And so they're essentially like holes within the superfluid leading sort of to a multiply connected region, at least within the mean field approximation. And you can see sort of the phase structure here and the density field in this. Now, the flow that's produced by these phase defects is essentially that of a point vortex flow field. So you just have a 1 over r dependence in terms of the velocity field with respect to distance from the vortex that's moving in the azimuthal direction. But because the phase is associated with sort of the exponentiate or the Madelung sort of transformed the representation of the wave function, then for the wave function to be single valued, it has to be an integer multiple of 2 pi always. And so that means you get quantization of circulation in superfluids, where the fundamental constant of the circulation is given by a Planck's constant h divided by the atomic mass m. And it turns out it's enough to just focus on plus or minus winding numbers, because any vortices with a higher winding number will just decompose into multiple vortices with a lower winding number because they are unstable. Now, what I'm going to now focus on is assume that we have a system where we have a gas of vortices. So we have many of these vortices in the superfluid, but they are well separated. And if they're well separated, then first of all, I need to sort of clarify what I mean by well separated. So we're thinking of vortices that are at distances sufficiently large from one another in relation to their core size or their healing length. And in that regime, one can show through some kind of asymptotic arguments, a systematic derivation, which I'm not going to sort of focus on here, that you can recover just the point vortex dynamics that describes the motion of the vortices at leading order. And so the vortices in this approximation will just be given by this Hamiltonian description of the point vortex, the classical point vortex model. And that's what would be an unbounded domain. And if you have boundaries, you have additional term to account for the fact that you have to satisfy the boundary conditions. Now, the important observation to make at this point is that the vortex positions determine the state of the vortex gas. Okay, so the configuration of the vortices is directly related to the energy. You do not have any term that looks like a kinetic energy term that depends on momentum. And that's an important observation. The reason is because now if you consider a Bose gas where you have many vortices in the system, so this is, for example, an illustration of a Bose condensate, a 2D Bose condensate with many vortices produced at Monash University, then what you can try and do is invoke a statistical mechanical framework to understand the properties of this condensate. And recognizing the phase space of the system is the configuration space, what it implies is that the phase space of the system is going to be banded if you look at the motion of the vortices in a banded geometry. So you can define a phase space volume as a function of energy in this way, and you can relate it to the statistical weight that usually is a quantity that appears in statistical mechanical descriptions. And so this phase volume, when you differentiate it to recover the statistical weight, will have this typical kind of feature here, which is rather peculiar, because on the left here, there's a positive slope, whereas on the right, there's a negative slope. Now, when you recognize that the statistical weight is related to the entropy of the system through Boltzmann's equation, then you can invoke thermodynamic relations and differentiate S with respect to energy, and recognize that this is just the inverse of the temperature. So what it means is that on the left here, you have positive temperature states, whereas on the right here, where the slope is negative, you have negative temperature states. Now, when you go far to the left, you end up essentially with a system that's dominated by vortex pairs, vortex-anti-vortex pairs, which is where the BKT transition that's studied in many experiments on these systems resides. But when you go far to the right, you end up with a regime where you have vortex clusters dominate. And this is the regime we're more interested in because it has been studied less so in these systems. Now, having recognized one can invoke a statistical mechanical framework to analyze this system, you can adopt a mean field theory of the point vortex gas. And so you introduce this coarse-grained description in terms of the number density of the vortices. And then from that, you can show by using, again, just standard results from statistical mechanics for calculating the statistical weight, and then coarse graining, you can show that the entropy can be expressed as a functional of this number density, and it takes on this form. Likewise, other conserved quantities like the energy and the angular momentum, if you are, for example, in a disk geometry, you will have angular momentum conservation as well. And so the Hamiltonian can be written in terms of the number density times the stream function, which can be decomposed in terms of the Green's function associated with point vortices, which is a logarithmic interaction. Right, now, the next task is to maximize the entropy subject to these constraints. And so you apply a variational principle, and you try to find really the extreme of the entropy subject to the constraints of fixed energy and angular momentum. And so these now have associated Lagrange multipliers with them. So beta is the Lagrange multiplier for energy, and omega is the frequency is the Lagrange multiplier for angular momentum. And so from that, you recover an equation that describes the equilibrium states of the vortex distribution. That's the so-called Poisson-Boltzmann equation that describes the stream function in terms of the number density, and the number density itself obeys this Boltzmann distribution here. Now, this argument works when you have a vortex gas of a single species, and typically, and for more general superfluids, you can have vortices of different signs, so you have to generalize to a two-species vortex gas, and all of the arguments that I presented can be generalized in a straightforward manner. So the subscript A here just denotes the different types of vortices, whether they have a winding number of plus or minus 1. And you can then just reconstruct the entropy in the same way and recover an expression for the vorticity. Right, now having formulated or come up with some kind of theoretical framework to try and understand the equilibrium distributions of the vortex gas, we wanted to see whether it's applicable in various contexts. And so we were motivated by this early work that was done by people in the University of Queensland and Monash University, where they started off with an initial configuration of vortices in a 2D Bose condensate, and they simulated this. And so what you're seeing here are vortices and anti-vortices moving around from a Gross-Pitaevskii simulation. They annihilate, and as they annihilate, the vortex density drops significantly, and then you end up with two large-scale structures. And so what's happening is the energy of the vortex gas is decaying, but the energy per vortex is increasing, and so you're migrating into negative temperature regimes. So we wanted to see whether we can explain this through the Poisson-Boltzmann equation. And so we, for this particular case, we end up with this essentially nonlinear eigenvalue problem here, where lambda that's related to the temperature plays the role of an eigenvalue. And you can have multiple solutions because of the nonlinearity of the system. So when you solve for this problem, you find several different solutions that are all local entropy maximizers. But the ones that correspond to the maximum entropy are the ones with the fewest number of cells in them, so that would correspond to this one here. So what we did is we took these vortices and we tracked their location, and then we were able to use the point vortex description to reconstruct the instantaneous streamlines of the vortices, and did a short time average to sort of invoking sort of an ergodicity hypothesis to relate time averages to ensemble averages. And this is what we saw from our simulations of the dynamics of these vortices. So the mean field predictions and the simulations seem to agree remarkably well. Now, over the years, the capabilities experimentally have moved to such a point where they can now do all kinds of trapping potentials. So a box trap that was first realized in the group of Zoran Hadzibabic, that's here in Cambridge, and I believe some of you may be visiting the lab tomorrow. But also I've started collaborations with people at the University of Queensland, and I've now sort of learned that they can use these so-called digital micromirror devices to imprint sort of arbitrary patterns on these BECs. And so it allows them to design Bose-Einstein condensates with sort of arbitrary potentials and try to inject vortices in a very controlled way. And so this basically paved the way to study 2D vortex dynamics. Right, so given that, we wanted to relax some of the assumptions that we were working with in terms of, for example, circular geometry. What happens if you relax to a square geometry? And we found that for the square geometry, you get two types of solutions, a dipole and a monopole. But when you compare the entropies, the relative entropies of the two, then you find that in the square geometry, the monopole seems to dominate over the dipole configurations. And so you'd expect to see this in numerical simulations. So we went ahead and set up a numerical simulation of a point vortex model using Hamiltonian dynamics, but with what we call a punctuated Hamiltonian dynamics. So we mimic the process of vortex-antivortex annihilation through pair removal. And we started with an initial condition like this, and after some time, the system evolved into this configuration here, and you saw the dipole and the point vortices, which when you time average, you see the dipole configuration. And at later times, if you wait even longer in the same simulation, then you see the monopole emerging. And so it did seem to indicate that the validity of the Poisson-Boltzmann equation in making predictions about the system were valid. And likewise, we did the same type of simulations with the Gross-Pitaevskii equation, where now you have vortices moving in a bath of phonons. We tracked the vortices, we did the same kind of processing, and we saw, again, a dipole at intermediate times and a monopole at later times when you wait longer. And so it all seemed to work consistently. Right, so about 2 or 3 years after we published this work, so the experiments Queensland moved on to the point where they were able to inject clusters of vortices with sort of, in a very controlled fashion, inject vortices with sort of different configurations, different energies, and so forth. And so this began sort of to pave the way of, well, can we make links with their experiments and test the validity of this theory? And that hasn't really been fully tested in any sort of fluids context. And so even though they were sort of typically injecting 10 to 15 vortices, because they were averaging over many realizations, they could build good statistics. And so we wanted to assess whether the system does indeed achieve equilibrium and what happens if you start from a far from equilibrium initial condition. Now, one of the challenges that we had to deal with is the fact that for the neutral gas, you have the complications of vortex-antivortex annihilations that can occur at intermediate times. Vortices can escape through the boundaries of the container. And then the detection of the type of vortex you have is not so trivial on superfluids. And even though experimentalists have come up with clever ways of trying to detect them, typically the phase is not does not correspond to a Hermitian operator in quantum mechanics, so it's not easy to measure the circulation. So they suggested, let's focus on the chiral vortex system in a disk geometry. And at first, this might seem sort of too simplified, But it turns out that Smith and O'Neill studied this problem in the 1990s and recognized that there is an interesting transition that takes place in this system. And so basically they found that as you vary the temperature of the vortex gas, you move from a Rankine vortex patch, where the edges then are smeared and you get more like a Gaussian distribution. And then you get what's called a Riccati vortex, and all of these cases can be solved analytically. But then at some point, as the vortex distribution becomes more and more peaked, it becomes impossible to satisfy the constraints of energy and angular momentum conservation. And so the only way that the system can continue to satisfy both is for asymmetry breaking to occur, and then the cluster has to move off-center to maintain conservation of angular momentum. And so this was predicted, as I said, by Smith O'Neill. And so given that, we tried to explore the entropy energy curve more closely. And this clearly shows that there is a bifurcation here where there is another branch that emerges with a higher entropy state. Now, because we can also simulate many of these things with the Poisson-Boltzmann equation, it turns out there are other branches that you can explore with lower entropies, and these can form good candidates for initializing the system in these states. So they are far from equilibrium, and then you can study how the system relaxes as you move towards equilibrium. And so this provides sort of exciting opportunities for experimentalists to explore these type of phenomena in their system. So what they did in their experiment is they sort of tried to explore the phase diagram of the vortex gas. So here you have the energy and the angular momentum are the two conserved quantities in the system. And you can see these markers here. So there's 5 of them. There's one here, another here, and then 2 in this region. And these are basically the experimental configurations I studied. And you have 2 off-center cases, and the others are the 3 centered ones. And so the way they did this is they used sort of these paddle stirrers where they rotated the laser beams in some like counterclockwise direction, and then they ramped down the amplitude of the forcing to leave vortices within the system. And so they ended up with clusters of vortices in different locations. So they could be off-centered, they could be centered. But typically you find that you have around sort of 10, 15 vortices. But they were able to reproduce these experiments over and over to build up many realizations and to build good statistics. And so with that, given that they've been able to measure these vortex densities, we wanted to compare now with the predictions of the Poisson-Boltzmann equation. And so the first comparison is shown here. And so what you're seeing here is the density of the vortex gas that's measured experimentally. This is solution of the Poisson-Boltzmann equation. And the 2 graphs here correspond to integrating along this direction or along that direction. And so the markers represent the experimental data, and the curves represent the solutions of the Poisson-Boltzmann equation. And we use only 2 fitting parameters for the Poisson-Boltzmann equation, the inverse temperature and the angular frequency. And so with just these 2 fitting parameters, we were able to reproduce their experimental measurements to such precision. Now, this was actually quite striking because we thought that given the few number of vortices, even though we are averaging over many realizations, that there would be significant amount of noise and we would need to adopt Monte Carlo type methods. And in fact, that's what we started off doing initially. But then when we found that the mean field solutions do work so well in this system, and they also allow us to explore states with lower entropies, we continue to sort of adopt them for further comparisons. And so these are other cases corresponding to different types of sweeps that were performed to inject vortices. And again, you see excellent agreement. And then here, this is the other cases that correspond to the Gaussian and the near-Riccati solutions, where basically you're crossing from positive to negative temperatures. And again, you're seeing good agreement. Okay, so this demonstrates that many of the sort of predictions of the Poisson-Boltzmann equation works quite well. But you might also be critical and say, well, you're injecting these vortices into the system near equilibrium, and you're not really demonstrating sort of true thermalization. And so we looked at this other case where they used this double stirring or double paddle stirring, to inject 2 clusters of vortices. And we recognized that it seemed that the initial vortex distribution seemed to correspond to a metastable state of the Poisson-Boltzmann equation. And we were able to fit the initial vortex distributions with these profiles by, again, just using these 2 fitting parameters. And so given that we were able to fit it at the initial time, and then we're able to fit it at later time, so this configuration after some time evolves into this. So you can see it's a truly out of equilibrium sort of evolution where the clusters merge and you end up with a single cluster. We were able then to actually extract the entropies in the initial configuration and the final configuration because we can just read it as solutions of the Poisson-Boltzmann equation. And what you're seeing here is that the entropy is 0.574 in this case and 0.928 in this case, so the entropy clearly has demonstrated a significant increase. And so it was demonstrated that the system does thermalize en route to equilibrium. Now, in a lot of these systems, true equilibrium is really when all the vortices have decayed and there's no vortices present and you just have phonons moving around. But the point is that this vortex gas essentially has conserved quantities associated with it, and when they are interacting weakly with phonons, they become adiabatic invariants. So you do not get rid of these vortices so easily, and they can persist for very long times, and they can slow down the process to true thermalization. And so with that, I'm going to end here and just summarize by saying that we have demonstrated that we can describe these equilibrium states of the vortex gas using a mean field description based on equilibrium statistical mechanical arguments. And what's interesting is that it seems to work both for the point vortex model, but also for the more sort of realistic Gross-Pitaevskii model, where you have interactions of vortices with phonons present. Just recently in the work that I've mentioned, which appeared sort of at the beginning of this year, we were able to demonstrate excellent agreement with experiments. And this is probably the first detailed comparison that's been demonstrated between this model and the vortex gas. And so future directions will be focused on trying to explore sort of true out of equilibrium phenomena. So for example, people are interested quite extensively in this program on the so-called soliton gas for integrable systems. And can we derive sort of equations, kinetic equations for the vortex gas and try to understand its implications. And with that, I'll end. Thank you.
Thank you, Hayder. Great talk. Questions? We do have time.
Thank you for that lovely talk. Very interesting. I'm really wondering about your ability to quantitatively make predictions for boundaries in the phase diagram and to quantitatively validate the use of mean field theory. Even in the Davis paper, he does say that in this, is it called Rankine configuration, that you expect some quantum Hall effect and mean field theory should break down. So in general, as we know, these vortex cores have a non-mean field component which support them, and that can affect some of these rotational dynamics.
Well, so first of all, I mean, I think the quantum Hall effect, from my understanding, when it's been studied in the context of these soft rotating vortex systems in bosons and condensates, they end up, I think it's more akin to the dense vortex limit. So you have, it's no longer a vortex gas, it's more like maybe a vortex liquid. So it's a very large density, and you get then strong correlations associated with that. So whether this framework actually is applicable on that limit is not clear. In terms of the actual, motion of the vortices, it's true when you have true many-body, or a more quantum mechanical description. There are certain aspects of the modeling here that are not accurate, but I would say that the leading order effects in this regime that we're exploring is well captured by a mean field description.
Yeah, no, I agree completely with that. My question was, can you use boundaries of the phase diagram to uncover some beyond mean field effects in mean field experiments? Might this be a situation like the LHY corrections in quantum droplets, right, where there is some significant change that may appear right on those boundaries. So if you really zoom in, you don't try to get just sort of order of magnitude or plus or minus 10% for the experiment or whatever it is, but you really try to be precise, where you could uncover some unseen many-body effects.
Yeah, I mean, it's difficult to say. I mean, I think, so there was some interest along this direction. I mean, I think when we were adopting Monte Carlo methods to try and get a handle on the phase diagram, there were some kind of additional effects that are not captured by the mean field description. And so perhaps that's a way to explore this. But whether, in terms of the experiments, whether they have sort of the experimental capability to really explore the phase diagram at that level of detail is not clear to me.
For example, you could calculate the shift from the LHY. Can I just interrupt? Sorry.
This discussion can continue afterwards. Yes. Let me give an opportunity to somebody else to ask questions. If there is, yeah, no problem. Any further questions? Yes.
Thanks, Hayder. Just a quick one. With this, the eigenfunctions you saw in the square, and it passes through the dipolar one before it gets to the monopole, is that because the dipolar one has lower entropy? And can you estimate the time it takes to pass between those two?
Yeah, so, well, so actually, I mean, what happens when you look at the dynamics is that the system seems to kind of undergo rapid transitions between the different cases. So it could spend some time in the dipole. It will spend most of the time in the monopole, but then it might flick back and spend some time in the dipole again. And in fact, this was actually very clearly observed when we studied, so when we deformed the aspect ratio slightly, and you can begin to bring the two branch of solutions together, because when you exceed a triangle with a certain aspect ratio, the dipole overtakes the monopole. And so when they're very close together, you can see the transitions occurring, and you can measure it in terms of some dipole moment or something like that. So it is driven by fluctuations, and I think the more vortices you have, the longer it will spend in a certain state before bouncing back to another.
Great. If there are no further questions, oh, there is one. Okay, please.
Very quick one, I promise. Can you just show again, if you showed it, or comment on when the transition, the symmetry breaking transition occurs for temperature and the other Lagrangian multiplier? Does it occur only on negative temperatures?
So you're talking about this?
Yes.
Yeah, so we are already in the negative temperature regime here where it occurs. We didn't pick out any other types of bifurcation there.
So you need to be at negative temperature and then at sufficiently high W, omega? So.
I think, I mean, so things are normalized such that the transition occurs when omega is 1, essentially. So, yeah, so there's like a kind of a universal curve that you're seeing there, but it always arises on this side of the curve.
Okay, thank you.
Right. So please join me into thanking all the speakers of this morning and Salman. Okay. We break for lunch now, and I guess the session starts at 2 p.m.